transformation. And now is the point to put in power the full conformal transformation. So imagine that I have a certain correlator, so an endpoint. So they will be definitely can be encircled by a circumference here. So imagine that I do a transformation which is infinitesimally everywhere. So this cannot be analytic function. Okay. However, I can choose this object to be analytic, say, in certain domain. So this means that under this transformation, this object is not going to be 0. So this is the point I was stressing yesterday. Invariance of a theory means that the variation is 0 for certain things. Not invariance is the variation is different from 0. The key point is that not if 0 or 0, if we are able to understand what is on the right hand side. Okay? So we should be able to pin down what is here. Once we do it, we obtain an identity which is called word identity. Word in this case has no responsibility. It's a general name that people assign to relation in field theory. We just come from change of variables. Indeed, it's just change of variables. So why so? Because you have to understand what this object is. So this object is some kind of path integral with certain field. I mean, it's not the same here, but certain basic field on psi, insertion of your object, and measure. Okay. I included the measure also the normalization downstairs. So when I do this change of variable, this is just change of variable. The effect of the change of variable, however, is on two pieces. Because under this transformation, there is a variation of the field, which actually we computed before. But there is also a variation of the measure. Since the transformation is not conformal, the variation of the action is not 0. But we know what it is. It's the stress energy density. Okay? So the strategy would be to understand what's going on in here, making a change of variables, and tracing back the variation that is responsible, where the field is responsible for this variation, and the variation which comes from the action. Okay, so let's try to do step by step. So first of all, the variation reaction. So we have some on the data. Okay, out of this computation I want to show you another byproduct, alias the splitting of Z is the back part that I claim many times. Okay, so what I'm doing? I'm doing the, how to say, the full variation of this object. Actually, as a matter of fact, here I was a bit sloppy. If I do a change of variable here, the result has to be altogether 0, because I'm just changing how I count the point. However, what I meant before, which I was a bit sloppy, is that this variation, global variation, involves two terms. Something which involves really the variation of the correlation function itself, this one, but then there is an extra piece coming from the measure, which is not invariant. Okay? Before, when I used measures, this object was invariant, so it never counts. The stress energy tensor was completely upset in the story, and therefore I get a differential equation. See, before I imposed the same object equal to 0, but this term was not there. Therefore, I got a differential equation from my correlation function. But if I do a generic transformation that cannot be small everywhere, well, the conformal invariance is broken. So I'm using something which is analytic here with something which is not analytic outside. So this term comes from an integral on the external region of this sphere. Okay? And then now I have to, here I conveniently at this point is still a notation. I just denoted epsilon bar, the right combination x plus iy, x minus iy. At this stage, it just change of variable, no implication whatsoever. But I'm already using a notation that at the end will prove to be correct. And then I start massaging this expression. Well, first of all, I can use the fact that this object I can integrate by part, but the stress energy tensor is divergenceless. So all this integral on the volume outside here, where I have no conformal invariance, can be reduced by the theorem on divergenceless field to integral on surfaces. At infinity, this field goes to 0, so remain just the integral on the surfaces here. So let me take this one, 2 pi I hope is clear the notation. This one is the element on the surfaces, this is the normal to the surfaces, and this was the value of the function there. Now, we remember that T mu nu was a symmetric tensor and classless. So it's a 2 by 2 tensor, symmetric and tensor, and traceless. So it has only 2 independent components. And these 2 independent components are the following. Actually, you can prove by the divergenceless condition, is this, and then you can make change of variable here to go to z and z bar coordinate. You can prove that this equation implies that this field is purely analytic, alias if you take dz bar, this object is 0, as well as if you take dz of this object is 0. Okay? So this is the reason why I denoted that this combination of components is dependent only on z and not on z bar, while this depends on z bar but not on z. The result comes from the divergenceless of the stress energy tensor specified with z and z bar. Okay? Which is an extra piece of information. Okay? So once we do that, I can, and this is just a trick, really a vulgar trick, how to say, something that you see, that an integral on a circle you can convert in an integral on a complex plane. Right? So this integral I can write very simply like 1 over 2 pi I contour integral dz of epsilon z dz whatever was minus 1 over 2 pi I integral del z bar t bar z bar what was inside. Okay? So I'm just saying here you have epsilon 1, epsilon 2. By epsilon 1, epsilon 2, you can combine epsilon 1 plus I epsilon 2, epsilon 1 minus I epsilon 2. This guy also in combining these things, and the corresponding integral, very conveniently, you write in terms of contour. Okay? And so this for what concerns this part here. But then we have to take care of this other part. And now we go back to our probably second year course of mathematical physics. You remember Professor Riemann together with Cauchy. And we remember how to convert an object like this in contour integral. Right? Alias, if you want to have delta d epsilon over dz plus epsilon d of something, this is as much as contour integral del z game is if you have a pole in complex analysis and you integrate around the contour, you pick up the value of the function there. If you have higher power, you pick up the corresponding derivative. So you see, if I integrate this term here, what I extract is the value of the function at the point epsilon where it was transmitted. Time the derivative on the function. On the other hand, if I want to get the derivative of epsilon, I just have to integrate the second order pole. Okay? Now, you can do the same here with the corresponding minus sign. And so at the end of the day, what we have, you see the structure start to become pretty obvious. We have an identity which looks like this. Integral dz over 2 pi I epsilon z sum of e delta e z minus z square plus 1 over z minus z delta e minus del z bar 2 pi I epsilon z bar delta bar I z bar minus z bar I square plus equal, I'm bringing everything on the other side, del z 2 pi I epsilon t minus del z bar 2 pi I okay? Yeah.
Is there not another part when you, because you turn the derivative over epsilon with 1 over z minus m1 squared?
Yeah.
But when you do that, you can choose to derive correlation function on the right.
No, because the zi are fixed. What I'm integrating on are the epsilon z. The point other where zi fixed. I'm not doing anything. So you see, this is the equation you get, which is an integral equation. However, epsilon is arbitrary. As well, epsilon bar is arbitrary. And so this means that Tz is 1 Cm is equal sum as well as the other one which concerns the z-bar part. Okay? Now you look this equation and you realize that there's some magic has happened. Because you have been able to set up the first non-trivial operator for expansion of theory. Because since this hold for any is an operator relation which read like this. The stress sentence, the analytic part, together with any primary field, fulfill an operator per expansion of this form, remember the general form. The general form was scaling field Pn, Z1, Pm, Z2, is equal to sum Cn, M, P, 50. Okay? So you see that here we are stating that the stress energy tensor together with a primary field has an expansion that whose maximum pole is a second order pole. We will see that this is a very distinguished property of the primary field. If you do not have primary field, the operator per expansion with T has arbitrarily higher order pole. The primary field is the mildest possible singularity, which is a double pole, plus single pole, plus something which we cannot fix. Why? Because I got from an integral equation to integrand, an identity between integrand. But in Cauchy integration, all regular power are zero. If I integrate, they give zero, no rest. Okay? So I can pass from here to here only for what concerns the singular part. But the regular part is not fixed. If you look this one, what is the anomalous dimension of the stress energy tensor? How do you get it?
Because of the exponent there.
So this is the general form, no?
Mm-hmm.
So you see there is delta n minus delta p. This term is the same as here. So this means that delta n will kill delta p and remain delta n. But delta n refers to here, alias to the stress energy tensor, which is 2. And actually this is another deep property of a field theory, which is the following. If you have fields, generic field, the anomalous dimension, really, of interacting theory, generically have nothing to do with the engineering dimension. Okay? So engineering dimension is the one that you get just looking at the Lagrange. But the anomalous dimension is the result of all the interactions. The two things can be pretty far one to the other. However, if you have a field which is conserved or has a symmetry of your theory, the engineering dimension coincides with the number one. And the argument is very simple. The argument is, imagine that you have in your theory, and it's an example, right? So it's a general remark. Imagine that you have in your theory operators which fulfill, say, an algebra. The stress energy tensor field an algebra. It's the algebra of the lowest field. Okay? So when you have such relation, which is a symmetry of your theory, this guy can never acquire an anomalous dimension different from the engineering one. And the reason is that if I acquire different anomalous dimension, you spoil this relation, because this part is quadratic, this one is linear. Okay? So indeed, stress energy tensor will be rechecked by Nader theorem in dimension 2 as dimension 2, because the integral on the space is an energy, which is an inverse of length. Okay? So, and indeed, from this relation, you find out this 2. Okay? Now, if this object has dimension 2, what is its two-point function?
something that is with the fourth power. 1 over z1 minus z2 to the fourth power. With some
Clear to everybody? Because I said before, two-point function is uniquely fixed by the dimension of the field. Dimensions here is 2, so here I can only see 1 over z1 minus z2 to the 2 times 2, which is 4, times a coefficient, which in this case I cannot fix. You will understand why I cannot fix later on. And then by convention is called C over. Okay? C is called the central charge. And then here start the beauty and the juicy of all the story. Because the stress empty tensor is simultaneously player and referee for this game. At the same time, you play and you make referee. Because on one side is the one responsible for the conformal transformation. What is it? But on the other side is a scaling field as another one. The only thing is the dimension is fixed to be 2, and it's the only field which has this dimension. So, if this is the case, I can immediately write down what are the operator Floor expansion of the field with itself. Let's write it down together. So in any operator Floor expansion, the term which doesn't contain any field, alias the identity, is the one which refers to two-point function. You can immediately understand this, something which I didn't say, but you are smart enough to have realized yourself, is that the expectation value of individual conformal field are 0, but the identity. So what I'm meaning is, if I have such kind of relation, I'm not write down now all the corresponding power. If you sandwich this relation, if you take expectation value, you get such kind of stuff. Now my claim is all these objects are 0, but the identity. There are no expectation value in conformal field theory. Give me an argument.
Because there is the orthogonality condition.
Symmetry.
Symmetry, what do you mean?
Translation.
Translation invariance means that they might not depend on Z.
Rotation.
No, it means that you select a scalar operator.
Yeah.
We can choose to cancel infinity, right? So
It's a very, very basic argument. Absolutely basic.
It gives you a length scale?
Yeah. There is no length scale. Length scale is infinity. Mass is 0. Okay? So this means that this object, if this object has an operator dimension delta, by dimensional argument, this guy can be a constant, A, times mass to delta. Okay? But I have no mass. My mass are 0. Okay? So there is no length in the game. The absence of mass scale implies that all expectation value operators which doesn't have non-zero dimension are zero. So the only one which survives is identity. Okay? So this is the reason. So come here, when you go and match these things, all become zero except the identity, which indeed match with the fact that you have identity operator. Actually, there is a very nice rule of thumb in all these games, which as a matter of fact works perfectly if you study many other systems based on this, which are animals. And the animals are based on all these rules. So what you have to imagine is that these two objects, when you are fusing two guys and a third one, there is some kind of flow where there is conservation of charges, if you want. Okay? So identity is the quantum number of a vacuum. So if you look differently, this looks like particle and antiparticle, if you want, that you have created out of the vacuum. So if I do not have charge conjugation in my game, as I'm doing, because I'm presenting you the simplest version of the theory, you can complicate the life, but I'm presenting the simplest. So the charge conjugation of the field is the field itself. And so this explains why you have this orthogonality condition. Because orthogonality condition means that you cannot create out of the vacuum object which has a quantum number which are not shared by the vacuum itself. Okay? So all that being said, so coming back now to our point. Our point was the identity channel is uniquely defined by the two-point function. So TT has an identity channel, and therefore is C over 2, Z1 minus Z2, 4 power. What is next? Remember I told you, T is referee and player. If he is a player, the second order pole has a residue which is the dimension of the field who is playing.
So it's 2 over that.
Okay? Now we fix the second basic operator for Pasquale. D itself. Okay. And now start the really interesting part. Questions? Question?
Why there is not the third exponent, the z1 minus z2 to the minus 3 in the expansion?
What is the operator? Do you have any operator or dimension? Which dimension should have?
Should have minus 4.
So you understand the question your colleague is arguing, say, why you jump from 4th to immediately second, and why you didn't put a third order pole in this expansion. Now this expansion are dictated, so if I put a third order pole, the corresponding operator there should have a dimension which absorbs the extra power. Okay? So at this point, you should have an object of dimension
1. Yeah, exactly.
Now, if you have no argument to do that, namely, there are theories where this term might be there because you have currents. You have extended algebra with currents. So you have to be careful in that case. But in the setting I'm presenting, I have no reason to believe or no reason to put into the game that they have a current of dimension 1. So I'm excluding. If you want, this commitment of myself on the basis that I have no reason to suspect that there is a guy of dimension 1. Dimension 1, once again, is a very peculiar number. In all this game, you develop really a sensibility for numbers, believe me. When you see numbers, you really understand what's going on. So, dimension 1 is a very peculiar number. It means current, it means conserved currents. If, how to say, you have no reason to put them into the game, you will not put it. In any case, it will not be there anyhow, for other reasons that you will understand later wise. So in all this story is really, you go on in the theory, you get some result, you go back, you understand better how you have derived the result, and then you keep going. So I'm saying that you will see later on why the structure of this guy is precisely this. And now become very, very interesting to derive the quantum version of the Virasoro algebra. So the point is, there is an isomorphism between operator Floor expansion and usual commutation relation. Okay? So usually in field theory we are used to write down commutation relation. We are happy with that, and we try to find representation of them and so on. Here, you have noticed that so far I never introduced such objects, but I was quite happy always to work with operator co-expansion of this type. However, I want to show you that existence of relation like this or operator co-expansion like this are completely equivalent. How so? Because you take a field like and you expand, say, around the origin. Okay? Now, convention is the following. If you take any scaling field, phi, so the convention is the following. You take any scaling field, you expand in power law up to branch, which respect the same dimension of this field. And it is very convenient. So in the case of the stress energy tensor, I put 2. Well, how is the Ln obtained in Laurent theory?
Multiplying by z to the n plus 1. And then integrate.
Okay? And so, imagine I have this T1, this T2. And I want now to compute imagine I want to compute these things here. So this will be 1 over 2 pi I square the expansion I can get whenever I want, and the field is from this analytic. So I have and this is the first way of getting. Now imagine that I swap. I want to get ln. Okay? So the only thing I have to do is taking this internal contour and bring outside. Now you can move contour as much as you like, as far as you don't meet singularity. When you meet singularity, you can expand the contour as far as you keep residue. Okay? So I'm not going to do all the detailed calculation because it takes long. Let me just show you one of them. You see, TT is singular and the poles are here. Let me take care just of these things. So I will get three kinds of contribution when I swap the two of them. So let me just take care of these things. So the first term will be so ln, ln commutators. Taking care of the first term is C half to the fourth power. Okay? This is coming, so z prime minus z, the fourth power, and then I have z prime minus z1, z2 minus z2. Now, Cauchy told us that when I do the integration dl z prime of a fourth power, I shall get the third derivative of the function computed finally in z prime. Okay? So if you do this computation and then add the factorial, you get c over 12, 6 factorial, 3 factorial is 6, c over 12, delta z sorry, is the third power, so I have to take n plus 1, n minus 1, and then I get the function computed in z, which will get n plus n minus 1. But this last integral vanish unless n plus m is equal to 0, because the only term which is a residue is a simple pole. So this means become c over 12 n squared minus 1 delta n plus m. Okay? Now, if you do the other calculations, taking care of this, what will be the result? You see that when you have a second pole, you have a first derivative acting on t. So the corresponding integral will be something which involves power, but then involves t itself. But that was a definition of ln. Okay, so if you do carefully, my claim is the following: ln as commutators that you can extract just the way I did it is n minus n l n plus n. This was the classical part. But then there is plus c over 12 n squared minus 1 delta n plus n. So this is the algebra we are talking about. So this is the quantum algebra. This term here is an anomaly. I can show you why it's an anomaly in a minute. And observe that this term is absent as far as n here is 0, 1, and minus 1. You remember that L0, L1, L minus 1 were Möbius. So, for what Möbius is concerned, this term is not there. While for other value n, which means a generic transformation, they are there. So why this is an anomaly? This is very interesting, because once again, T is simultaneously player and referee. And remember that we computed before what was the variation remember what was the computation it is. The variation of a correlation function is as much as insertion of t. Okay? So the variation of correlation function is as much as inserting t. So this was our one direction. And now let me take for t exactly t. So the variation of t is okay. But this term is C half z to the 4 power. 4 power means that I'm taking here third derivative. Okay? Remember what was Möbius? Möbius was a polynomial at most of order 2. So if I get Möbius, the variation of t is 0. But if I take a generic transformation, my series expansion will be higher power than 0. Therefore, the third derivative of this guy will be different from 0. So why I call anomaly? Because if I apply a generic conformal transformation, I'm changing geometry. And if I normalize my vacuum expectation with 0 on the plane, will appear a non-zero energy density on a finite geometry. This has a name in physics, it's called Casimir effect. Okay? Because if I use, for instance, the map from the plane to the cylinder, L, here, if I have normalized my stress energy tensor, which the integral of it is the energy, now energy is up to additive constant. You have to decide where you normalize it. Typically, people normalize at infinity, saying I have 0 energy at infinity. What happens is that if you now compress your system, once you have normalized to infinity, on a finite geometry, there is a presence of a density of energy, just for the finite size effect itself. So in this case, this appears like an anomaly, and by the way, you can use this phenomena to compute the stress, the central charge itself, alias the expectation value of a strip is equal minus pi over 6 L squared. Okay? So in principle, if you do studies of finite size scaling of your critical systems and probing how the energy scale with L, has to be L squared for dimensional reasons, the coefficient in front is the central charge. The central charge we will see is the finger point of the different universality class. Actually, you can convince yourself easily because there are at least 2 examples where we can compute what the value of C is. The 2 examples are the free bosonic field and the free fermionic field. Say Majorana type. So here you have L, which is this one. From this you recover nature. From nature you have the stress energy tensor, which is something like this. And from here, from Majorana, you have something which is like this. And you recover as well the stress energy tensor from here, which is the C proportional. Then you apply, you have to compute 2-point function, and you just apply big T. Okay? So for fermions, you have something like psi 1, the psi 1, psi, the psi. You just do the contraction, keeping in account the different sign of fermentation. By the way, from fermions, the 2-point function is 1 over z minus z2. And this comes just from the inverse of propagator. But you see that when you get the propagators, this match perfectly the physical property you expect for fermions. Why? Because this object, if I interchange, has to change sign. So the propagator can only be odd functions, C1 minus C2. The simplest one is a simple pole, but simple pole means that the anomalous dimension of this guy is 1/2. Which is correct. Okay? Being a fermion to the mesh. So everything matches perfectly. So if you do these 2 cases, you find that for bosonic field, the central charge is 1/2. For Majorana is, so for bosonic field is 1, for Majorana is 1. And so the final result, as I say, I'm making for you a summary, is that after you develop completely the theory, you understand that the central charge is a measurement of the massless degrees of freedom that the theory has. So, and the rule of thumb is if you have 1/2, you have Majorana. If you have 1, you have bosons. Intermediate is kind of reduction of bosons. And then you can play with a lot of these numbers. So 2 Majorana fermions make a Dirac fermions. A Dirac fermion you can bosonize, as you have learned, and therefore the central charge of the 2 systems has to match. Indeed, they match. Okay? Now you probably know this result in string theory, when people say, well, string live in dimension 26, or superstring live in dimension 10, how the hell they reach this conclusion? For a very simple counting, because a string is just a spatial conformal field theory, where the fields are the coordinates themselves. Okay? Now, if there are just bosonic string, you have something which the action is the, say, sigma mu so you have a kind of dimension where here there is the coordinate of these two-dimensional fields, while the field are played by the coordinate themselves. Okay? But being a bosonic field, each of them count one. So if you have d dimension, you have a central charge d. However, in string theory, you have a huge invariance which comes from the reparameterization of these things. When you have such things, to fix the symmetry, you need ghost. I'm making for you a long story short. Ghost has central charge negative, they are ghost. The name means something. And their numbers is fixed. How much is it? 26. And if you don't want any anomaly, the total central charge has to be 0, indeed. If the central charge was 0, you have no anomaly. Therefore, for string requiring no anomaly, fix the dimension of your space-time to be 26. Okay? If you repeat the same computation together with fermions, other superstring, the fermions count 1/2 each, the bosons 1, you have corresponding ghosts coming from the fermions themselves, and the result, having the total central charge of 0, is dimension 10. This is how the people got the critical dimension string. Very simple. Killing the anomaly of the total conformal field. Okay? Okay, so we'll stop here, and then hopefully tomorrow we'll close.